All right, let's dive into an idea that's shaking up the very foundations of math and computer science. It's called homotopy type theory, and it's a totally new way to think about what mathematics even is. Now, to get why this is so revolutionary, we've got to start with a huge question. I mean, if you were going to build all of mathematics from scratch, what would you use? What are the absolute most basic, fundamental atoms of math? For well over 100 years, the answer to that has been pretty clear: sets. This system, you might have heard of it, Zermelo-Fraenkel set theory, or ZFC for short, it's been the bedrock. It's like the operating system that almost all of modern math runs on. So here's our game plan. We're going to start in that familiar world of sets, and then we'll see how homotopy type theory totally reimagines things as dynamic spaces. Then we'll hit its most radical idea, that equality is actually a path. We'll see how that leads to a superpower called univalence. And finally, we'll look at why this is such a game changer for computers before asking the big question: is this the future? Okay, so before we can appreciate the new, we've got to understand the old, the established world of set theory. And a great way to think about it is that sets are like the ultimate Lego bricks. The whole idea is that you can build literally any mathematical object, doesn't matter how complex, just by sticking these simple bricks together in different patterns. In this world, everything is a set. A group, that's a set with some extra rules. A function, that's just a set of ordered pairs. And notice, logic, the whole true or false world of propositions, and the world of sets, they're treated as two totally separate things. Now, this is super powerful, but here's where it gets a little weird. Because everything has to be a set, you get these strange statements. Like in the standard way we build numbers, the number 2 is technically an element of the number 3. It's a valid statement in the system, but it's completely bizarre. No mathematician actually thinks that way. And this is where homotopy type theory, or HoTT, comes in with a totally new angle. It doesn't get rid of sets, but it starts with a different building block, one that in many ways just feels more natural: the type. You see, in HoTT, a type isn't just a static bucket you put elements into. It's treated as a living, breathing geometric space. So think of the type of all circles. It's not just a list of circles. It's a space where you can actually imagine one circle smoothly deforming into another. And that idea, that concept of a path from one thing to another, that is absolutely key. Okay, let's really dive in, because this next part, this is the absolute core idea of homotopy type theory, and it changes everything we thought we knew about the simplest, most basic concept in all of math: the equal sign. So here's the fundamental split. On the left, in the old world of set theory, the statement A equals B is just a proposition. It's a boring binary fact. It's either true or it's false. That's it. But over on the right, in HoTT, A equals B isn't a statement, it's a type. And what kind of type? It's the space of all the paths connecting A to B. Suddenly, equality isn't just a fact anymore. It's this rich, structured place that you can actually explore. And this immediately leads to a kind of mind-bending question, right? If equality is a path, a way of getting from point A to point B, could there be more than one way? Could there be multiple different proofs that two things are equal? And the answer is a huge, resounding yes. But it gets even crazier. Just like you can have multiple paths between 2 points, you can have paths between those paths. They call this a homotopy. And then you can have paths between those paths and on and on and on, creating this incredible infinite tower of higher dimensional structure that was just hidden inside the equal sign all along. So this space of paths gets a formal name. It's called the identity type. And its elements, its inhabitants, they aren't true or false. They're the journeys themselves, the proofs of equality. They're treated as first-class mathematical objects you can actually work with. And this is where the homotopy part of the name comes from. It's the study of these paths and the paths between the paths. Okay, so this new, much richer idea of equality builds up to something even bigger. It comes with a kind of superpower. It's a fundamental rule of the system, an axiom, called the univalence axiom. The univalence axiom is this really profound, elegant principle. As the HoTT book, which is basically the Bible for this field, puts it, it connects 3 different ways of saying these two things are the same, but from 3 totally different areas of math. And here's what it does, and it's just brilliant. Univalence says that these 3 things that look totally different are in fact fundamentally the same. So first, a formal logical proof that 2 types are identical.
Second, one of these topological paths between them that we've been talking about. And third, something called a homotopical equivalence, which just means they have the same essential structure. It takes these three separate ideas from logic, topology, and algebra, and just collapses them into one powerful concept.
So what's the big takeaway here? In simple terms, it's this. Univalence makes a rule out of something mathematicians have always felt in their gut. The idea that if two objects have the exact same structure, if they're isomorphic, then you should be able to treat them as being the same thing. HoTT just makes that intuitive feeling into a formal, provable law. Now, I know what you might be thinking. This all sounds incredibly abstract, right? But it turns out it has a huge practical payoff, especially when it comes to computer proof assistance. You know, the software that helps mathematicians check their super complex proofs for any logical errors. Well, it turns out that trying to teach a computer real-world math using pure set theory is a nightmare. As one expert put it, it can be completely intractable. Why? Because the computer has to constantly unpack everything. It has to remember that a group isn't just a group, it's a set with some other sets attached to it. HoTT is just more natural. A group is a group. And because those proofs of equality are actual objects, these paths, the computer can grab them and work with them directly. And that's a massive, massive advantage. So, does this mean HoTT is going to replace set theory as the foundation of math? Well, the reality is a little more nuanced. It's a young field, it's still developing, and it has both incredible promise and some pretty big challenges. You know, on one hand, HoTT offers this beautiful unification of different mathematical worlds, and it's a language that's almost perfect for computers. But on the other hand, it's complicated. You can't just write down a short, simple list of rules like you can for set theory. And getting it to work for some classic areas of math requires adding even more new rules and axioms. It's very much a work in progress. And that brings us to a really great quote from the mathematician Andre Bauer. He says, "Foundations of mathematics are not a competition. Set theory isn't going anywhere. HoTT is really a powerful new language, a new set of tools that lets us see math from a totally different and maybe more geometric angle." Which leaves us with this one fascinating question to chew on. For a century, we've built our mathematical universe out of these dimensionless points that we group into sets. Homotopy type theory suggests that maybe we could build it out of vibrant, dynamic spaces full of paths instead. The question isn't which one is right, but which language will let us discover more.